where um, so this is 1,000 cells. Yeah. That means it's not a little bit, but this is 55. Yeah, I think this is actually 50. Okay. But once I got 55, my school on. Oh, okay. And it was just like total like 165. So right. So we'll discuss why that's happening for today. But then if your current number is going up, you need to reduce the time steps. And would that mean that I have to restart the whole mesh conversion steps? Technically, yes, but for this activity, I'm not going to report that. So just whatever trials you're in, just keep that. Just make note of it in your activity. For your final project, you want to make sure that you're using the same time step size for all. Is there kind of like a so, yeah, so there's a formula for the Courant number we went over last time. This is only approximate, it's not exact. But basically Courant number is that you take the velocity, you multiply by the time step size, and you divide by delta x, which is the grid space. So every time you refine the mesh, you're making delta x small, right? And so generally you want your Courant number to be less than 1. My stylus has been acting up a lot lately. Right? And so if you're going to make if you know that you're going to get your mesh down to a certain level with a certain size, then you should set your time step size to be, to be less, to make sure that this entire product is less than 1, right? And then for the velocity here, you would generally use like the maximum velocity in your simulation. I don't know why maybe I just need a new stylus. I'm trying to circle the U here, but it's not working. I dropped my stylus yesterday, which was not unusual. I've dropped it before, but then ever since then, it's been kind of really acting up. I replaced the tip and everything too. What if it's just you have too much text? I don't think so. This is a new page here, and this happened yesterday with another class as well. So hopefully hopefully it works today. It was working just a second ago. The old school, I have expo markers. Yeah, I was telling you I miss actually I only did it for a couple of semesters because I started working here right before COVID, but I do miss actually writing on the whiteboard quite a bit. But whiteboard doesn't actually work that well with Zoom, so that's why I kind of switched to iPad since then. But yeah, iPad is nice for its own its own stuff, but it also has its issues as well. I think it's better like this because sometimes professors when they write with markers, yeah, they're in the way, so I can't write. That's fair. That's fair. That's fair. But with the whiteboard, I have so much more space too. I can kind of write the whole thing. But yeah. There's also some, well, this one doesn't have, but then the classrooms where the whiteboard can you can throw it up, like those are fun. But yeah. Yeah, I think I just need a new stylus. Drop this one too many times. Probably would have been better to get a real Apple Pencil too, not just one off Temu. Okay. This sucks. My Apple Pencil doesn't work. It's gonna be hard to give the lecture today. Hold it in this specific form. Right. Hmm? Let's see.
Also, I noticed that like if the app needs an update, it'll do weird stuff like that.
I see. I see. Well, it's working if I just maintain this, so I just have to like script pencil really hard for the entire lecture today. So I can get a new one. I get one over the week.
You use my laptop.
That's okay.
That's me taking noting you hear me.
It's all good. I think we'll be okay.
It becomes too much of an issue. That's just better.
Oh, it's okay. There's not that much we need to talk about today, so I was thinking we might end early anyway. So okay, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so today is second lecture of week 13. So today I think will be the last, I think, kind of I would say kind of theory focused day. So after today, we're gonna, of course we have to take our midterm. But then after that, we're gonna pivot and just kind of focus on open phone, right? So I'm working on your guys' final projects, and so I do hope to have that ready. I'm also prepping the next open phone activity. So I know open phone was kind of just kind of crammed in kind of near the end of the semester, but I was kind of learning it right alongside you guys. And so the hope is that by week 14, which is basically the week after our midterm, then we're going to discuss. First of all, I'm going to present the final project to you guys, so you guys know what you need to do. And then we're going to do open form activity 3 as well. Okay. Then from then on, after the midterm, we'll only have 4 more lectures remaining. My plan is to do open form activity, and then just kind of have some time for you guys to work on the final project. Originally, when I started this semester, I had planned to, have you guys make accounts on National Supercomputer and run OpenFOAM on there. So I still want that option to be open, but I don't want to kind of force it because it's kind of a lot at the end. So you guys, I'm adjusting your final project so that you should be able to do it on your own personal computers. So based on kind of what I've seen from activity 1 and from what I've seen from people presenting activity 2 to me, you should be able to do it based on your personal computers. But the cluster will be there for people that want to really kind of scale it up and kind of really run with the much higher flash. Okay. Okay, so that's the plan kind of moving forward for the rest of the semester. Today, of course, will also be the last topic. Today's the last lecture of topics that will be on the midterm. So after today, there's, you don't have to worry about that. And then the information that you need today is what you're going to need for homework 5 as well. Okay. All right. Any questions I can answer before we get started for today? Yes.
So far, we have information for just the question 1.
Exactly. Yeah. 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 So today we're going to cover 2D applications for time marching. And technically, we haven't done one where you need to maintain a time variable too, which you need for problem 2 on the homework as well. So, we'll cover both of those today. Yeah. Okay. Any other questions? Okay. All right. So let's get started. Let's hope my iPad, my Apple Pencil will work here. Okay. All right. So first topic that I want to go over, we kind of got cut short on it last time, was the difference between explicit and implicit methods. I lost the grip. There it is. Okay. Okay. So far, we've learned 2 different methodologies for advancing a system forward in time, right? So we've learned explicit Euler and implicit Euler. Okay. Now, these are not the only time advancement schemes out there. In fact, there's lots of different time advancement schemes. But even the more complex time advancement schemes, they generally fall within these 2 categories. You'll have explicit schemes and implicit schemes. Okay. And knowing the difference between these 2 is actually something that is very important. And this goes beyond CFD as well. And so any kind of computational method that is going to simulate time-dependent phenomenon, finite elements is also in this category as well. The same kind of intuition, same methodologies kind of apply. Okay. So let's go over explicit first. So that was the first one that we learned. Okay. And so the benefit with explicit methods is that you obtain an explicit expression for the value for the solution at the next time step for every. All right, and so if you look back in your notes and you look back and see how our explicit Euler method was formulated, right? We had a formula like this. We had phi I n plus 1, right? The n plus 1 term in our recurrence relation was by itself on the left-hand side of the equation. Okay. And then on the right-hand side was all quantities that were already known. So they were either the solution at the previous time step, or they were things like the source term, right? So stuff that was. So I'm not going to write out everything again, but this was all known quantities. So there was no, you could technically compute an expression for everything that's known. Okay. All right. So because we have these explicit expressions under explicit Euler, generally when you run an explicit time marching scheme, your scheme is going to run faster. There's less computations involved in doing an explicit scheme. So since you do have an explicit expression, there's no need for any kind of matrix set of equation, matrix inversion solution to a linear system of equations, none of that mumbo jumbo, right? You just basically just form your expression and you just do addition, multiplication, subtraction, and that will get you your answer. Okay. So explicit time marching schemes are generally easier to implement. The downside to explicit time marching is that you are much more susceptible to instability. And in fact, for those of you that are already working on OpenFOAM activity 2, you may have already experienced this, right? Because OpenFOAM actually uses an explicit time marching scheme. That's the default. I think there are settings that you can use to change that. You can switch it to implicit, but if you don't set anything, the default is just to do an explicit time marching scheme. Okay. So for instability, right? So something that we kind of talked about at the very end of lecture on Monday was this concept of the Courant number. The Courant number is something that's output directly by OpenFOAM in a lot of different cases. Okay. The Courant number has a very simple expression. So the Courant number is just the product of the flow velocity multiplied by the time step size divided by the grid spacing. Okay. Okay. So generally speaking, when you run an unsteady simulation using an explicit scheme, the exact number for the exact number for the threshold for the Courant number depends on which explicit scheme that you're using. But generally, you want the Courant number to be as low as possible in order for a stable solution. The absolute threshold is around 1 usually. Okay. And so you definitely want to be below 1, but even for cases which are higher than or less than 1, you may still get unstable solutions, or the solution may start to diverge. Okay. And so you want to kind of really be careful about it. Okay. Especially questions.
So far, we've been working with only velocity direction.
Yep.
If you have velocity direction.
Right, it's a great question. So this velocity here is actually velocity magnitude. So you would take your velocity vector, even if there's multiple components, and you would take the magnitude of that. Yeah, it does get a bit more complicated because if you do have a velocity that's kind of skew, so it's not really aligned with your grid, that does change things a little bit. That's why I said you want your Courant number to be as low as possible, because if you're around 1, you're more susceptible to still be unstable if it can. But technically, this is velocity magnitude. Yeah, great question. All right, and so you have to be careful because the velocity is one thing in this expression, but another thing that should jump out to you is that you have this ratio of the time step size and the grid space. Okay. Now, if you think back to activity 2, right? Activity 2, one thing I'm having you do is I'm having you do a mesh convergence test. Okay. And so as you refine the mesh, right? So as you kind of increase the number of cells in your mesh, your grid spacing tends to get smaller. Okay. And so if your grid spacing is getting smaller, right? Generally, your velocity is going to be the same. Generally, you set your velocity boundary conditions at the beginning. You don't change it, right? And so in order to maintain the same Courant number, you have to lower your time step size. And so that's typically what you do when you have an unstable simulation. You have something that's just kind of blowing up, right? You run the OpenFOAM simulation, it starts to diverge, the simulation just crashes. The first thing I always tell people is, let's try reducing your time step size in order to get your solution to be stable. Right? So that's a very kind of important practical tip that you should always remember when you're doing CFD or any computational method is that the time step size is a big marker for student. It also increases your accuracy. And so reducing the time step size is always good. The downside, of course, that you reduce your time step size, it's going to require a longer time to run your simulation. So there's a balance. Okay. Unfortunately, we don't have time to get into the exact theory of why reducing the time step size increases your stability. But I think the easiest kind of qualitative explanation I can give is that, when your Courant number is greater than one, generally what's happening is that, the flow conditions are changing faster than the simulation can keep up, right? Because the simulation can only solve things one time step at a time. And so if your time step size is too big and too much is happening in between the time steps, then the simulation kind of gets confused and it kind of outputs kind of infinite numbers, which is not good. And so in order for your simulation to kind of keep up with the flow that it's simulating, oftentimes you need to reduce that time step size. Okay, and a smaller grid spacing actually makes it even more difficult to capture that phenomenon. Okay. So time step size with explicit methods, there is a very kind of strong relationship there that you should know. And just know that most codes, and this goes for finite elements as well. ANSYS is the same way. Most of the time, you're going to be running an explicit scheme, just because as you kind of go up in complexity, it becomes a lot more difficult to implement implicit schemes. Not to say that it's impossible, but explicit is just way easier, especially for an equation as difficult as Navier-Stokes. So you have a lot of things going on. You have the nonlinear convection term. You have the pressure coupling, right? And so a lot of times that explicit is just an easier approach to go. Okay. Okay. So that's the benefits for the explicit method is that it's much easier to implement. It's much faster when it works, but you do have to watch out for instability. Okay. All right. Any questions on explicit schemes? Okay. All right. By contrast, implicit schemes kind of fixes a lot of the issues with explicit schemes at a cost, of course, right? So the big benefit of using implicit schemes is that, dang it, I lost my grip. Okay. Spent too long yapping and then I adjusted my grip of my hand. There it is. Okay. Okay, so for implicit schemes, the benefit for implicit schemes is that they are much more stable. And so that means there is not as strict of a requirement on the time step size. And so that's huge, right? And so if you can use an implicit method and you don't have to worry about stability, that's obviously huge. And then you're kind of free to kind of choose a lot of other problem parameters that you wouldn't necessarily have the freedom to choose for an explicit scheme. Okay. Now, the downside to implicit schemes is that on a per time step basis, so just to compute the solution for one time step, it is a lot more expensive. And so if you remember from the last example that we did on Monday, right? Even just to compute the solution for one advancement, so for one time step size in implicit Euler, it required a matrix inversion operation. And that's not uncommon. Right? And matrix inversion, we're not really getting too much into the linear algebra in this class, but matrix inversion is incredibly expensive, right? And so if you compare that to explicit Euler, where we have an explicit expression, all it needs is just addition and multiplication and subtraction. Matrix inversion is orders of magnitude more expensive. Okay. All right. So having stability is great, but you do pay a very high cost for that in terms of computation. Okay. Now, sometimes this balances out, right? So because, a lot of times you don't have a strict requirement on the time step size, you can get away with having a very large delta t. Okay. And so if you think about the number of time steps that you need to reach a full solution, with implicit methods, it's often a lot less. And so yes, each time step is going to be a lot more expensive with implicit Euler, but oftentimes you're going to be running a lot less time steps overall. So the costs, sometimes can balance out. Okay. All right. And so then that begs the question of, which one is better? So are explicit methods or implicit methods better? Well, you could make the argument say that, explicit is the default in OpenFOAM, so that must mean that it's better. Um, you know, I would say explicit is easier, right? And oftentimes, when you're running a particular simulation, there are a lot of applications where you want your time step size to be small anyway. So regardless of the issue of stability, because oftentimes you're trying to capture phenomena that happen very, very quickly to begin with, especially if you're looking at things like turbulent flow, flow structures that don't last very long. And so oftentimes you want your delta t to be small anyway. And so if you're going to make a small delta t anyway, you might as well just use an explicit method. And I would say, the majority of practical cases kind of fall within that regime, where, regardless whether you're thinking about stability or not, there are other reasons why you would want a small time step size. And so in those situations where you're going to make delta t small anyway, your time step size small anyway, explicit is the better option, because then you're going to be computing, you kind of already resigned yourself to computing a lot of time steps. So you might as well make the computations as fast as possible. Okay. So if you're not sure, I would say explicit is usually the better place to start. Usually the applications that want to use implicit are usually very specialized. The one that really stands up to my head is if you have creeping flow. Right. And so, creeping flow is a type of situation where, you maybe don't necessarily care about the minutia of what's happening in terms of, moment to moment, but you want to kind of simulate for a long period of time. Right? So you're not just running a simulation for 10 seconds of simulation time. Maybe you want to run a simulation and it's going to simulate stuff that's going to happen over like an hour or 2 hours, right? So one application for that could be like weather modeling, right? So weather modeling, oftentimes you're interested in kind of the bulk movement of certain kinds of weather patterns and bulk movement of kind of, large, weather systems that are going to travel over long stretches of, more long distances over long periods of time, right? So you're looking at a simulation that takes place, between like 8 a.m. and noon, right? And so if you did an explicit method for that, you're going to be simulating probably like 1 million time steps. Yes, each time step will be fairly cheap, but it's going to take a very, very long time to run that simulation just because there's just a lot of computations involved. Whereas, if you know that you're going to be running a simulation that's going to simulate 4 hours, maybe your time step size would be something like 5 minutes or something. And then, you can use an implicit method where you don't have to worry about stability, but it does get you to the end, much, much faster. Okay. So think of explicit, implicit, not as one that's superior than the others, but, as different tools that are utilized in different applications. Okay. Any questions on explicit versus implicit time marching before we move on? Okay. All right, so let's do another example. So this example is going to be similar to problem 2 on the homework. Okay. So this example is going to be the first time that we're going to do a problem where time actually appears as a variable in the problem itself. Okay. All right, so we're actually going to look at the exact same problem that we've done this example 3 times now. So we're going to look at unsteady diffusion. Okay. We have partial t is equal to 3 partial squared phi partial x squared. Okay. Right, so we have a simple unsteady problem. We have a diffusion constant of 3, and we just have diffusion here, so no convection. Okay. All right, so we need to list out the boundary conditions. So this is where things are going to change. Okay. So previously, in the last 2 examples we did, our boundary conditions were constant, so they did not change with time, right? And so this time we are going to actually change them. So phi at x is equal to 0 for all times t. Okay. We're going to have an oscillating boundary condition here. So we're going to say that our Dirichlet boundary condition at the inlet here, or at x equal to 0, is equal to cosine of pi times t. Okay. So that boundary condition is actually going to change with time. And then for the second boundary condition, this one will actually stay the same. So we have d phi dx at x is equal to 1, all times t is equal to 2. Okay. All right, and then just like before, we have our initial condition. All right, so we're going to assume that we start with a 0 initial condition. Okay. Okay, so for this problem here, I'm not going to go through the entire thing again, just because we've done this. This is the 3rd time that we've seen this example, but I do want to show you how you're going to make the adjustment. For situations where time actually shows up in your problem parameters, just like it does in your problem. Okay. Okay. And so let's use explicit Euler. I don't know why I put it in lowercase, but I guess we're disrespecting Euler. That's fine. Okay. It's okay. Euler's long dead. You can't haunt me now. You can't give. Okay, and so just like before, we need our time step size, we need our grid spacing. So let's say that our time step size delta t is 0.1, and our grid spacing delta x, we'll say is 0.25. Okay. All right, so just like we did before, we can basically use our explicit Euler equation, right? And so since we have since we have a grid spacing of 0.25 and the length of our domain is 1, right? So just like our last two examples, this means we have 5 grid points, right? And so that means for each of our grid points, we're going to have a time advancement equation, right? And since we're using explicit Euler, it's going to be an explicit equation. So you have I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. Okay. We have phi I n plus 1, or phi 1 n plus 1, excuse me, phi 2 n plus 1, phi 3 n plus 1, phi 4 n plus 1, phi 5 n plus 1. Okay, so we can go ahead and plug in the values for this problem, right? We know that whatever we plug in for explicit Euler is only going to apply to the interior nodes, right? So it's only going to apply to nodes 2 and 4, right? 2, 3, and 4, excuse me. And then for nodes 1 and 5, we're going to apply our boundary conditions. Sorry, I was just looking at what the coefficients are. I'm trying to do it all left-handed because I don't want to mess up my grip on this pencil. Okay. All right, so for nodes 2, 3, and 4, let's go ahead and write those in. So we plug in the numbers for this problem, right? So we have k is equal to 3 here, u is equal to 0, right? So we plug those in. So this is from example 1. We get 4.8 E1 and at n, excuse me, minus 8.6 E2 at n plus 4.8 E3 at n. Okay. Next, we have 4.8 E2 at n minus 8.6 E3 at n plus 4.8 E4 at n. So all those are the same. So I'm not really going to focus on those just because those we've done before. Okay. Okay. But what I do want to focus on is the boundary condition, okay? Because this is one where something is going to change with time. Okay. Okay. So according to our boundary condition here, right? Phi 1, or basically the value for phi at x equal to 0, is equal to cosine pi times t. Okay, so the way we write this is that, we write out the function. So this is going to be cosine. Okay. But we're going to apply it at the current time step, right? So that Tn there, that Tn, we say is the current time for this particular time step. Right? And each time you advance, or each time you march forward, that Tn is also going to be marching forward in time as well. Okay? Because remember, delta t, right? Delta t is the parameter that tells us how much time is going to pass in between time steps. Okay? So we always start at time is equal to 0, right? So our initial conditions are defined at t is equal to 0. But as soon as we march forward once, the next time step that we're computing is going to be at t is equal to 0.1 in this case. So delta t is 0. Right? Okay, actually, let me write in the formula for the last equation here. So remember, this is our Neumann boundary condition. And so since d phi dx is 2 here, that means our last boundary condition here is going to be 0.5 plus b4 to the n. Okay. And again, that was from our first example. Okay. So let's advance this forward a couple steps. And I'm going to, just kind of put the emphasis on that phi 1 up there. Okay, so at t is equal to 0, right, we have our initial conditions. Plus boundary conditions. Okay. All right, so t is equal to 0 is always a little bit special, when you're doing this, just because you mainly just use the initial and boundary conditions to determine your values here. Okay. Okay. So let's go ahead and write all those out. So at t is equal to 0, we have phi 1, phi 2, phi 3, phi 4, phi 5. Okay. All at the first time step. So we're going to have this all at 1. Okay. So initially everything here is 0. So we're going to put zeros everywhere. Okay. Right. So all those zeros are meant to represent our initial conditions. But of course, for the first phi value and the last phi value, we're going to adjust their values based on the boundary conditions. Okay. Okay. So phi 1, we're not going to do that. So instead, we're going to set this equal to cosine of pi times t at 1. Okay. For t1, we're just going to plug in whatever the current time is, right? So when t is equal to 0, we're going to plug that in there, right? So for this particular time step, t is equal to 0. So it's going to be cosine of 0 times pi, which of course is cosine of 0, which is just 1. Okay. All right. And then for the last node here, we have our Neumann boundary condition. This one doesn't change with time, but it's just simply equal to 0.5 plus phi 4 at 0. Okay. Where phi 4 at 0, we're just taking our initial condition here, which is 0. So that means phi 5 at the first time step is going to be 0.5. Okay. All right. Any questions on that? Okay. All right. So let's move on to the next time step, and then let's see how the time variable here is going to update. Okay. Okay. So at the next time step, our current time Tn is going to advance forward. It's going to march forward one time step. Okay. So Tn started at 0, right? Now, after we advance forward one time step, Tn is now going to be, it's stepped forward by 1 delta t. So Tn is now going to be 0.1. Okay. So basically everywhere in our problem where we have time, we're going to plug in 0.1, which only is in the boundary condition at this point. Okay, so just like in the previous step, we're going to write out all of our phi values here. So phi 1, phi 2, phi 3, phi 4, phi 5, this time at the second time step. Okay. So I'm not going to write out the values for phi 2 through 5 because those are practically the same as before. The only one I'm going to focus on here is just the first one because that one is different. Okay. Okay, so for phi 1 here, we have cosine of pi times Tn. Okay. Now Tn is updated, right? So Tn is no longer 0. Tn is now 0.1. Okay. So we plug that in, we get cosine of 0.1 times pi. Okay. All right, so I don't have I do have a calculator, but it's just kind of the details at this point. And so, would then update the value for this based on that value there. Okay. Now, what you'll notice here is that this is now changing with time, which makes sense because time was a factor in this boundary condition. Okay? So we have a situation now where our Dirichlet boundary condition actually does change with time. Okay. And then everything else, not that they're not important, it's just that we've kind of seen them before. So, just to be a little bit efficient on time, we'll kind of save those details for later. I just want to focus on just the part change. Okay, so we'll go forward just one more, just so that you can see. Okay, so after we solve all that, we can advance one more time step. Okay. And so once again, we're going to increment, but we're going to update Tn. We're going to say it's going to march forward in time by one more step. Okay. So every time we advance a time step, we add delta t to our Tn. So if Tn was 0.1 in the last time step, now it's going to be 0.2. Okay. And so that means our value for phi1 at time step 3 is going to be cosine of 0.3 or 0.2, excuse me, times pi. Okay. And then everything else kind of stays the same. Okay, so that's how you deal with a problem where time is a variable. So it's it's not that big a deal, and so the only thing you just have to make sure is that you just continue to update that time variable, and you're aware of kind of what it is for any given time step. Okay, any questions on that? Okay, good. So last thing that we're going to talk about today is unsteady problems in 2 dimensions. Okay. So in terms of calculations, there's not too much we can actually do here by hand, just because 2D problems are a lot bigger. And so, it's not that we can advance this forward in time. Too many steps, right? And I'll tell you right now that on the exam, there is no 2D problem for time marching. So this is purely just for your homework and just for your own information. Okay. Okay. But the technique that we're going to use is actually no different than what we did for the 1D problems. It's just that there's just a lot more to do in 2D. Okay. And so just like the 1D problem, we're going to start with the full conservation equation with all of its partial derivatives. We're going to replace all of them with their finite difference approximations, and then assign a time step to each of the parts based on whether we're doing explicit or implicit Euler. Okay. Okay. So let's go ahead and do that. And let's do explicit Euler for this example here. Okay, I guess this is not an example. This is kind of more of a derivation. Oh, I'm lost my thing again. Oh, my pencil's dead. My pencil's like, it's time to go home. You know what? The battery just might be bad here. I have just charged it. Okay. Okay, so oh, there's back. Okay. Second wind. Okay. Okay, so let's use explicit Euler on our 2D equation here, right? So let's write out the full equation first, and then let's discretize it according to our method. Okay? All right, so we have partial phi partial t plus u partial phi partial x plus v partial phi partial y, okay, is equal to k, our diffusion term, which is partial squared phi partial x squared plus partial squared phi partial y squared plus q of x and y. Okay. So I think this is the first time we're seeing the entire conservation equation with every single term all together in one place. So this will be the first time we solve it all together. Okay. Okay. All right. So let's go ahead first. Let's do finite differences. Yeah, so we're going to replace every single derivative here with the finite difference approximation. Okay. Starting with the time derivative, right? So that's going to be phi I comma j minus phi I comma j. First term here is n plus 1. Second term here is at n. We're going to divide by delta t. Okay. So that's our finite difference approximation for the time derivative. Okay. Next, we have u. We have a first order derivative in x. And so for this, we're going to use a central difference scheme. So phi I plus 1 comma j minus phi I minus 1 comma j all divided by 2 delta x. Okay. Since we're doing explicit Euler, we need to assign a time index for this derivative. Since we're using explicit Euler, we're going to assign a time index of n. Okay, so both of these are going to be at time index n. Okay. Because remember, with explicit Euler, we only want one n plus 1 term in the entire equation. Okay, and we're going to do the same thing for the y derivative. The y derivative, we have v. Once again, we're going to use central difference. Phi I j plus 1 minus phi I j minus 1 divided by 2 delta y. Both of these, once again, evaluated at time step n. Okay. All right, these are equal to k. Second order derivative. And so second order derivative, remember, we only have one option for this. So this is phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j, all evaluated at time step n. Divided by delta x squared. Plus the same thing for the y derivative. So phi I j plus 1 minus 2 phi I comma j plus phi I comma j minus 1, all divided by delta y squared. Okay. All of these also evaluated at n. Okay. So with 2D problems, remember the main difficulty is just there's just a lot of terms. And so you would definitely want to be make sure that you're getting all the details right for this, all the signs and everything. Okay. Okay. And then we can't forget our source term. So our source term is q, x, and y. And so for that, we're just going to add q at xi, y, j. Okay. Okay. So now we have to do a bit of algebra here because we've gone ahead and plugged in everything, which is good, but we want to rearrange this so that it's in a useful form for explicit use. Okay. Okay. So let's go ahead and rearrange the terms. Okay. So in particular, we want to isolate the n+1 term on the left-hand side, and there's only one here, right? Okay. So we're going to isolate the n+1 term on the left-hand side, and then everything that's evaluated at n, we're going to move to the right-hand side. Okay. So since every other term here is either the source term or it's the solution evaluated at time step n, all of that is already known, right? And so it gets moved to the right-hand side because of that. Okay. Okay. So let's go ahead and do that. So first thing we need to do is we need to multiply everything by delta t. Okay. Okay, and so we do that, we get phi, comma j, and +1 is equal to, okay. We're going to move our two convection terms over. So I guess let's move the time step term first. So this is going to be phi, comma j, evaluate n, okay, minus u delta t divided by 2 delta x, right? phi+1, comma j, minus phi-1, comma j, both evaluated at time step n. Okay. Same thing for the y velocity. So this is minus v delta t divided by 2 delta y. phi j+1 time step n minus phi j-1 time step n. Okay. Plus k delta t divided by delta x squared. phi+1, comma j time step n minus 2 phi, comma j time step n plus phi-1, comma j time step n. Okay. Nice. So that's the x diffusion term. So we need to also do the same thing for the y diffusion, which looks very similar. The only thing is that the +1, -1s, those are going to be on the j index instead. Okay. Right, so then we have the y diffusion term. So this can be a plus k delta t divided by delta y squared. All right, pen died again. Come on, pen. Wake up. Hmm. Okay, pencil's not waking up again. Okay. There's not too much more after this, and so let's so I know this is not ideal, and unfortunately it stopped right in the middle of when I was writing. But let's go and switch to Dropbox here. Okay. Okay, so let's go to 436 spring lecture notes. We are on time marching notes here. I don't want to rate this. Okay. So we're on this set of the lecture notes right here. So we're basically, taking our, explicit Euler method, we're applying it to 2D convection diffusion. Okay. So this is where we started. Okay. So we started with an equation, partial phi partial t plus the convection terms, plus the diffusion terms, plus the source. Okay. And what we did is, we just did this. So we basically took our, we took each of our derivatives there and we plugged in their finite difference approximations. Right, so everything I'm highlighting here, those are the finite difference approximations. So that is these last two things I highlighted, those are the convection terms. Then we have the diffusion terms here. Okay, so you wrote this down already. Okay. And then we were in the process of simplifying, right? And so by simplifying, we're first of all, we're moving everything that is not n plus one, we're moving that to the right-hand side. Okay. Right, so this is the convection term, so we just already wrote that. Okay. We have the x diffusion term. So the x diffusion term is k delta t divided by delta x squared times phi I plus 1 at n, comma j, minus 2 phi I, comma j, plus phi I minus 1, comma j. Right, there's, I don't have it here, but there should be an n on that term as well. Okay. All right, and then we were just in the middle of writing this term right here, right? So let me go ahead and erase these. Okay. All right, so the y diffusion term, coefficient out in front is going to be a k delta t divided by delta y squared. Okay. So that delta t came over from the left-hand side that came from the time derivative, and we're multiplying it by this expression right here. So phi I, comma j plus 1 at n minus 2 phi I, comma j at n plus phi I, comma j minus 1 at n. Okay. Okay. And then finally, we have our source term. Okay. And so our source term is very easy. There's not too much to implement here. It's just whatever our source function is multiplied by delta t. Okay. And also, in the equation I was writing in the class just now, this phi I, comma j at n, I moved this to the front of the equation, but this right here came from the time derivative term. Okay. All right, so that's step one of the derivation here. So we're just simplifying. So last thing we're going to do, right? Technically, we can use this equation as it is, but usually the most convenient thing is to group the like terms together. So so that we have a coefficient in front of each particular neighbor. So you should have a coefficient in front of the left neighbor, in front of the right neighbor, the north neighbor, the south neighbor, and the south term. Right? Okay. And so that's what we're going to do on this last step here. Okay. Okay, so I did kind of the algebra for you, and so this is the last expression here. And so you can see we have phi I, comma j n plus 1. That is isolated on the left-hand side. On the right-hand side, first we have the coefficient in front of the left neighbor. Okay. So this right here is our left neighbor, or west neighbor, I guess you can say. So the coefficient for the west neighbor is u delta t divided by 2 delta x plus k delta t divided by delta x squared multiplied by phi I minus 1, comma j at time step n. Okay. Right. So that is our our neighbor on the left-hand side or the west side. Okay. Okay. And then after that, we go ahead and move on to the right neighbor. So the right neighbor is this expression here. Okay. So it looks very similar. It's just that the sign of the convection derivative is opposite. So we have a minus u delta t divided by 2 delta x plus k delta t divided by delta x squared multiplied by phi I plus 1 at n, comma j. So this right here is the right neighbor. Okay. All right, and then we have similar expressions for the south neighbor and the north neighbor. Okay, so we come down here. Next term we have, let me just kind of erase these. All right, next term we have, not now spam. Okay, next term we have the south neighbor. Okay. So the coefficient for the south neighbor is v delta t divided by 2 delta y plus k delta t divided by delta y squared. And that is multiplied by phi I comma j minus 1 at n. Okay, so that is our south neighbor. Nice. Okay. Forgot to put on do not disturb. Okay. Okay, and then we have the north neighbor coefficients. And so we have a minus v delta t divided by 2 delta y plus k delta t divided by delta y squared multiplied by phi I comma j plus 1 at n. So this right here is our north neighbor. Okay. Okay, so I find this form a lot easier just because, oftentimes when you're presented with the problem like you are with the homework, you have the values for the convection velocities, you have the values for the diffusion constants, you know what the grid spacing is going to be, the time step size. I put in this form just to make it kind of just very easy to kind of plug and shut. Okay, so you have just a singular coefficient for each unique neighbor, so that when you start time stepping, you know exactly kind of what to plug in. Okay. All right, so that is the coefficients for all of our neighbors there. We also have a coefficient for the center node as well. Okay. So the center node coefficients is given by this expression right here. Okay. So for the central node, we have a minus 2k delta t divided by delta x squared minus 2k delta t divided by delta y squared plus 1. So this is the coefficient for the south. Okay. So, it might seem strange to see the same phi I comma j on both sides of the equation. But remember, this one is evaluated at time step n, right? So this is technically at the previous time step. So this is something that's known, right? And all this is really telling us that, the solution at our current time step is going to affect the solution at the next time step as well, which makes sense, right? Right, so where you are currently will depend on where you are next, right? I can't just teleport on top of CS because I'm currently here. Okay, and then finally, the last thing that we have in our expression is our source term. Okay, so this last term here is our source. Okay. So our source term is just qi comma j, which is just the source term evaluated at the two, at xi and yj multiplied by delta t. So the delta t comes from the time. Okay. All right. So there's a lot of terms here. I know it looks intimidating, but it's basically the same 5 variables. It's just kind of repeated in different ways. Okay. So to do these 2D problems, and we'll go over kind of the homework after this, just because the example I have is not that great, just because it's it's mostly written for code. But we'll go over that in a second. Any questions on this expression here? This would be the explicit Euler equation for 2D convection diffusion. Let me actually write that down. Feels so clunky to write with my fingers compared to my hand. I feel like Shrek. Okay. I believe the homework has you do explicit Euler for 2D, just because it's, how to do implicit Euler for 2D would be a little bit cruel. Okay. Okay. All right. So let's take this equation here and let's actually apply it to a problem. So let's actually start the homework, just because I think the example that I have down here is not that good. Okay. All right, it's not bad. Actually, let's do this example just so the homework is a bit more of a surprise. Okay. Okay, so for this example here, we have the following equation. So the equation that we have here is partial phi partial t plus 50 partial phi partial x plus partial phi partial y is equal to 3 times our diffusion term, partial squared phi partial x squared plus partial squared phi partial y squared plus 3xy. Okay. Oh, be back. Let's see. We're back. My pencil is back from the grave. Okay. Okay. So let's kind of work with this equation right here. Okay, so this is the problem that we're doing. I know for this example here that we have a two-dimensional a two-dimensional domain here with with 30 grid points in each direction. But just so that we can do hand calculations, let's split this up into the very typical kind of 16-point grid that we have here. Okay, so we have a two-dimensional domain. This is point 1, point 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So on the homework, I've given you a problem that's very similar to this, where I give you a grid, I give you an equation, and I want you to compute the explicit or time advancement for all the nodes in this grid. Okay. 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 So first thing we're going to do is we're going to determine what all the values of the parameters are in this system. Okay. All right. So reading them off the problem here, we can see that u is equal to 50. Okay. All right. So u is the x velocity. It's just whatever coefficient is in front of the x, the first derivative with respect to x. Okay. V, which is the coefficient in front of partial phi partial y, is just going to be 1. K is going to be the coefficient in front of the diffusion term, which is 3 in this case. Oh, and his pencil is down again. Okay. It only showed up for just 5 minutes. That's okay. Okay, so K is 3. Okay. And this time we actually have a source term as well. So a source term is going to be, I don't know why it's not letting me draw again. Let me go ahead and re-enter here. Okay. So source term is 3xy. Okay. Okay. So this problem here, just because this example here, I've kind of designed it to be for code. There's no explicitly given delta x, delta y. But you can imagine, for a 4-point grid like this, delta x is going to be 0.25 as well. And then delta t here, we can assume to be 0.1. Okay. Now, even my finger is not working. Let's do this. Try relaunching Dropbox here. Okay, good. Okay, so let's assume that delta t here is 0.1 and delta x is 0.25. Okay. So those aren't given to you in this problem, but for the homework problem, I believe that it was given to you. Okay. All right, so we're basically going to plug everything, all the parameters in here into this equation up here, right? So we can have, u is equal to 50, v is equal to 1, k is equal to 3, and then delta x, delta y, or delta x, delta y, and delta t are given below here, okay? Okay, so you plug all those in, right? It's just a matter of kind of plugging and chugging here. eventually you're going to end up with an expression like the following. So, phi I plus 1 or phi I comma j n plus 1 is equal to some coefficient a phi I minus 1 comma j n, so on and so forth, right? So you're going to have a numerical coefficient in front of each of the phi values there, okay? And then the way you would use it is that you would advance forward just like we did before, okay? So you basically, plug in different values of time. You start with the initial conditions, and then you advance forward, okay? The only thing to be careful of here is that, in 2D, right, our boundary conditions are a little bit more complicated, right? So if we go back and we draw our grid from before, okay? So we draw our grid like the following, right? Right? So our boundary conditions are applied on multiple nodes here. So we have a boundary condition on this node, this node, this node, this node, this one, this one, this one, and this one. Okay. All right. So we're applying boundary conditions on more than just two nodes here. And so, this is going to be nodes 2, 3, 5, 6, 7, 8, 9, and then 10, 11, 12. And then 13, 14, 15, okay? So you're gonna have boundary condition equations on all of these nodes here, okay? All right, so just make sure that you are aware of that when you're doing the homework, okay? But for all the interior nodes, and so for, this node, this node, this node, this node here, right? For those nodes, you're going to be applying our explicit Euler time advancement scheme for those interior nodes there, okay? And remember, because we're doing finite differences, right? Of course, we have our corner nodes, okay? Right, so nodes 1, 4, 16, and 13. But remember, for the corner nodes, we don't actually account for them in finite differences. We kind of just ignore them, okay? So technically speaking, even though this is a 16-node grid here, you should only have 12 expressions or 12 advancement formulas for your explicit Euler, okay? And then beside that, you use it exactly the same way as before. So you start with the initial conditions, and you just kind of keep plugging in until, you reach the amount of time steps that you need for the solution, okay? Okay. Any questions on that? Okay, all right, and so that's all the time we have for today, or that's, I guess, all the content I have for today. So I apologize for the technical difficulties. I guess this pencil is it's lived its lifetime. I've had this since COVID, so I guess that's pretty good for a pencil here. So I'll have a working pencil again by Monday. So next Monday we are going to start something new. It's not going to be something that's on the midterm, but it is something that's important for the final project, which is verification and validation. Okay, so we'll talk about what that means practically for CFD simulations in general, and then next Wednesday we'll take the exam, right? And then after Wednesday, after that, like I mentioned, everything from after the exam is going to be dedicated to just OpenFOAM and the final project. Okay. All right. So thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you guys on Monday. Yep. Sure.
On the open phone.
Mhm.
You're not telling me enough, but this is like this back to previous.
So that's probably an issue with the block machine. Oh, inherit. Interesting. You and you were use stealth. Okay, so remember, that's beautiful. So remember, when you run OpenFOAM, you can have the velocity that are defined at the cell centers. And you have the velocity that are defined as the node. So when you run a glyph, click on the glyph. So you're scaling it based on the points, right? And so if you click on this, click on that down arrow there, right? So you can either pick U point or U cell. So the fact that they're matched there should mean that it's okay. Let me see the message. Mismatch. Can you click on the arrow next to it? Let's see what it's referring to. Let me see the green line again. Okay, so yeah, it's complaining about the glyph, but you have both as the cell, both as the points, and even the coloring is also good as well. Let's see if they use anywhere else. So go ahead and scroll down a little bit here. You can try deleting the glyph and then making it again. But the figure looks fine. I think this is one of those warnings where I think you can kind of just and just kind of take the screenshot from there. But these results look great. So if the message is bugging you, you can try remaking the glyph.
Okay.
It doesn't look like anything's the issue here, because I mean the glyph has formed, which is fine. But for some reason it thinks that it needs the cell attribute, but it's using the point. But everything here is consistent, so I can see why there would be an issue. Maybe click on channel flow.
Because I even
okay, so this one is using the cell one, so maybe change this one. So those might have just been the errors before. So I think if you want to, you can kind of just just restart pair view here, and then just make sure that you're always just using this. So it doesn't matter if you cell or point, they give you the same thing. But just try to be consistent with kind of everything.
okay, because I tried to do that and do like when it first popped up.
Yeah.
It's when I started doing even the point.
Yeah.
I started just getting all this. I'm just like, okay,
I see. Yeah, it's nothing's wrong. I think. I mean, the simulation ran well. It's doing exactly what you expect it to do. I think it's just something with the outputs that it's things that's misspent. But yeah, it's one of those warnings. So this one you can, as long as you're producing the image, it looks reasonable. Then you're on.
Okay. Okay, sounds good.
Yeah.
Yeah, I was when I was concerned on Monday because just disappeared. And I was like, back.
Oh, I
was
see.
like,
I see.
What is going on here?
Yeah.
I'm not sure if it's like well from the other just
Paraview is kind of weird. Yeah, Paraview it's a free software, which is kind of amazing in the fact that it does so much, but it's still free, but it still acts like a free software. It'll do weird stuff like that. Weird ones, but as long as you can get the plots for everything, then that's all we use Paraview for. So it's all good.
Yeah, I think that's another question too. Is it possible to add parts into OpenFOAM?
Yes. So that is going to be OpenFOAM activity 3.
Okay.
So OpenFlow activity 1 and 2, we created kind of our own box and channel flow. But ideally, most of the time you want to add your own like SolidWorks part in there and do compute flow. And that's what most people want to do. So that's what we're going to do in activity 3. The reason I kind of waited for that is that the mesher for that is a little bit finicky. So we're going to use a tool called Snappy X Mesh. It is difficult to use. And so I'm first of all, I'm trying to find a problem that's simple enough, that's consistent that we can do in the lecture, but also complex enough so that when you try it on your own stuff, you kind of know what to do. And, there's a lot of common pitfalls. So yeah, it's taken me actually quite a while to do. But yeah, the answer is yes. It's just hard. Yeah.
Professor.
Yep.
Have a good weekend.
You too.
I had a question myself.
Yeah.
Assignments.
Sure.
Yesterday I tried getting as much as I could have done with it. And up until question problem 2, like I got the graphs and everything side by side.
Okay.
I know you wanted it as a CSV file.
Yeah.
I downloaded or
for this that's okay, but for the final project, I do want kind of cleaner looking.
Okay.
But for this that's fine.
Okay, because I tried saving it and then for some reason it doesn't appear on my files or anything. But for problem 3, every single so I got it right the first time. I was able to get the values, the pressure, everything, the cells. When I tried running it again with the modified like initially it was like 20, 20, and 1.
Yeah.
I did 25, 25, 1.
Yep.
In the block. For this, it gives me the cell for 6,750, but every single time I run it like for pressures, it gives me this.
Yeah. So what's happening with your simulation is that it basically became unstable. It diverged. And so so one thing we talked about today, let me actually bring up the notes again. So what can happen when you have an unsteady simulation? You are kind of subject to something called the Courant number. And so the Courant number is basically this quantity right here. So we have U, which is the velocity multiplied by delta t divided by delta x. And so when you refine the mesh, you're actually making delta x small here, right? Because delta x is the size of your cell. And so what can happen is that if delta x is getting smaller, then you're actually getting pushed towards more instability. So to balance it out, you actually need to reduce the time step size, delta t. So if you go into control dictionary, one of the files that's in the system folder, there is a parameter for dt. Try lowering, try making that half what it is, and then try rerunning your simulation, and then you should be stable after that.
What do you mean go into whatever it was you just said? You mean where the vertices in the block is, or
No, so that's block mesh.
okay.
So there's another file in there called control dictionary.
Okay.
And so open that file, and then there is a list of parameters. And so actually, let me bring it up here. Actually, let me stop the Zoom. I'm listening to our whole conversation here.